purpose of this course is to examine how modern science has led us to redefine reality. But before we can talk in detail about redefining reality, we need to chat about the original definition. Now, during the 20th and the beginning of the 21st centuries, we've seen stunning advances in science, from relativity and quantum mechanics, from neuroscience to microcomputing and imaging technologies. What makes these advances so shocking is that they challenge basic beliefs about the nature of reality that are so fundamental they seem self-evident, necessarily true, unrevisable. And yet, our best scientific theories have forced us to reconsider them and envision a world that is quite different. In order to feel the full impact of these modern advances, we need to feel the pull from the view of reality that preceded them. Before we can understand what it means to redefine reality, we need to set out the original definition of reality. Now, it's unfortunate that science, since the end of World War II and the beginning of the Cold War, has been taught in a largely ahistorical fashion. With the threat of nuclear annihilation, the launching of the space race, and the technologizing of the global economy, the emphasis in science education has been focused on cranking out as many qualified scientists and engineers as possible, as quickly as possible. Add to this the fact that all our sciences have advanced rapidly and splintered into detailed subfields, and the result is that the history of science has gotten squeezed out of the way we teach the sciences themselves. But there's much to learn from the history of science. When you learn science, the rejected theories can seem quaint, if not absurd, and it's valuable to see why smart people bought into them. It's also helpful to see the residue of old ways of thinking. What invisible presuppositions do we still accept despite having surrendered the worldview that produced them? Rethinking these is often the key to the route forward. So, let's start with the birthplace of the pre-modern Western view of reality, classical Greece. It's truly stunning how much of an understanding the ancient Greeks had about the universe and how intricate their theories of physics, astronomy, chemistry, and biology were. Many of us were told when we were young that Christopher Columbus in the 1490s, in addition to finding a shorter route to the east, was trying to prove that the world was round. But the fact is that the ancient Greeks knew back in the 4th century BC not only that the earth was round, but knew to a staggering accuracy how big it is. They used a couple of means to calculate the circumference of the earth, but one straightforward approach used nothing but a pole, a ruler, and lots of cleverness. Now at noon, the sun's at its highest point in the sky. Hold a pole vertically and it casts a shadow on the ground. But what happens if two people conduct this experiment at different places? Now if the earth is flat, the shadow should be the same no matter where you are, since the angle will be the same. But if the earth is curved and one of the poles is north of the other, the angle changes because of the curvature of the earth. So they tested it, and lo and behold, the lengths were different. They had proof that the earth was curved. Combining some intricate geometry with knowledge of how much farther north one person was, the Greeks calculated how big the earth is. Brilliant! The idea of a round earth situated itself well in the Greek view of the world. On the one hand, it's squared with the observable facts. The sun rises and sets in the same directions day after day. The moon rises and sets in the same directions night after night. So too with the fixed stars. The repetitious motions certainly seem circular. The idea of a round earth with heavenly bodies moving around it in their own circular orbits seemed to make for an elegant picture. That elegance was important to the Greeks, whose worldview was based on the concept of teleology. Now, the word teleology comes from the Greek words telos, which means an end, a goal, or an aim, and logos, which means reasoning, logic, or intellectual order. Teleology is the view that all change is goal-directed, that everything happens because of an end that's trying to be achieved. The universe, they believed, was well-ordered and striving for a goal, namely perfection. When a thing is perfect, it's reached its goal and will never again change. But until then, it'll seek a higher state on its way to its goal. Now, note that we still have plenty of remnants of this view in the way we speak about science today. Matter seeks its lowest energy state. Evolution selects advantageous adaptations. The economy moves towards stable equilibrium points. All of these are framed in the sort of teleological language we get from the Greek thinkers. It's this view that led Plato to express his famous picture of reality set out in the allegory of the cave in his masterwork, The Republic. This view contends that there are two worlds, distinct realms. One is the material world, which is ever-changing. A material thing can always change. Just give me a big enough sledgehammer. This means that the material world will never be perfect, always corrupted and corruptible. But the other domain, the realm of ideas, is different. All material things are part of a species, a type, a kind. What defines that species is a set of essential properties. To have real knowledge of a thing is to understand this essence, or form, as Plato called it. Wisdom comes from rejecting the imperfect representations of the forms, that is, the material things, and embracing the immaterial forms, the perfect, unchanging ideas of the things. In Raphael's famous painting, The School of Athens, the great thinkers of classical Greece are seen together. At the very center of the image are Plato and his student Aristotle. Plato is pointing up, while Aristotle is portrayed pointing down. Where reality, according to Plato, is away from the material world in the world of forms that can only be viewed with the eye of the mind, reality for Aristotle was right here in this world. It was Aristotle's elevation of the material realm that launched what we think of as science. Now, Aristotle studied for decades with Plato at his academy until Plato's death, after which Plato's lectures became intolerably boring. He knew Plato's thoughts inside and out, but he wasn't a disciple. He rejected certain important core elements while he did keep other central aspects. One of the features that Aristotle shared with Platonic thought, and so many others of these Greek thinkers, was teleology. Right? Again, teleology is the view that everything in reality strives towards a goal, a perfect, unchanging state. Right? Again, for Plato, this perfection lies in the world of forms, a realm accessible only to the mind, but not the senses. Aristotle, on the other hand, puts them here in the observable world with us. All things are a part of a species that's defined by its essential characteristics. Crucially important properties that all members of the species share. These, according to Aristotle, are internal, in that every member of a species shares a certain structure of their soul, all have the same potentiality, and naturally grow in the same way to actualize it. Aristotle thus undertook the project of cataloging biological creatures and systematically ordering them by anatomical properties. Carl Linnaeus followed up on Aristotle's work in the 18th century, giving us our modern taxonomy of living things. This essentialism also served as the basis for Aristotle's theories of chemistry and physics. Now, because of our modern atomic theory, we think of chemistry emerging out of physics. But for Aristotle, it was the other way around. All material things are comprised of four basic elements: earth, air, fire, and water. It's interesting that today, references to these four earthly elements takes on a sort of new age, anti-scientific feel, a sense of rejecting modern science. From our contemporary atomic view of matter, the old elements do seem kind of silly. But it makes a lot more sense when we realize that they're reflective of what we now call states of matter. Earth, or soil, is solid. Water is liquid. Air is gas. And fire, that seems to be a thing unto itself. And we now know it's a chemical reaction, rapid oxidation. But it has a location, fire is in a place, and it has a size. So it seems to make perfect sense that we would think of it as a type of thing, as a fourth kind of matter. Now, when we said that all things were made of earth, air, fire, and water, what we meant was that all things were in one of these four states. and that chemical reactions brought on by mixing or heating or cooling could give rise to a new substance in a different state. Basic chemistry. Each of these four elements had an essence, and this included a natural place. The place in the universe where it was meant to be. So when Aristotle says that Earth is at the center of the universe, he's not making what we think of as an astronomical claim, that the planet Earth is the center of space. Rather, he was simply making the true claim that dirt falls. By Earth, he meant soil. If I have a clod of dirt in my hand and drop it, where does it go? Straight down. But recall that the Greeks knew that the Earth is round. If it goes straight down, no matter where I am, then it's always moving towards the middle of a sphere. When Aristotle says that Earth is at the center of the universe, he means that soil will seek its natural resting place and remain there, and that place is at the center of the universe. Water, too, moves straight down. Tip over a cup of water, and it spills down in a line. But water's place is not at the center, right? Greece is comprised of a peninsula and islands. They knew all about water, and that dirt settles out to the bottom, and water sits on top. So, the natural place for water is in a sphere around the natural place of Earth. Dunk your head under the water and exhale, what happens? Bubbles come out and move straight up. Air has a natural place above water. If you flick your Bic, the lighter will cause a small flame. Turn the lighter upside down and what happens? You burn your thumb. Why? Because the flame is always going up, no matter the orientation of the source of the fire. Fire is seeking its natural place above the sphere of air. All of the earthly elements have a natural place, and their natural state of motion is in a straight line to that place where they then remain at rest. Motion is caused by an internal drive within the object based on its nature. According to Aristotle, all of the objects close to Earth are made up of these four elements. But extraterrestrial objects, the moon, the sun, the fixed stars, these are made of a different kind of stuff. Ether. Ether is a more perfect element, and so objects made of it take on a more perfect shape, the sphere. Symmetry is not only beautiful, but an indication of perfection, and the sphere is the most symmetrical and thereby the most perfect three-dimensional shape. And so, all of the heavenly bodies are perfect spheres. Their trajectories? Circles, the most perfect two-dimensional path. Because of the perfection of their constituent makeup, their behavior would be perfect too, right? Ether is perfect, so their shape and their motion has to be perfect. The problem for Aristotle is that we know from observation that we couldn't use simple single circles to account for the observations we collect. The planets, for example, will occasionally exhibit retrograde motions. Their movements will seem to move backwards from the motions they previously exhibited and relative to the fixed stars. The sun does rise and set in the same way every day, but the point on the horizon where it rises, that changes each day, moving forward and back through the year. So Aristotle, as well as others of his time like Eudoxus, a fellow student at Plato's Academy, they tried to multiply the circles, giving us epicycles or circles on circles. We could imagine this as spheres rolling around each other. Claudius Ptolemy, writing in Alexandria in the 2nd century, finished this project, creating the greatest work of the ancient world, his masterpiece, the Almagest. This book contains a complete account of the motions of all of the objects in the night sky viewable without a telescope and perfectly describes their trajectory. To get this degree of accuracy, Ptolemy relied on some intricate mathematical tools. Epicycles, circles and circles, and then circles and circles and circles. Eccentricities, squished circles, and ecliptics, off-centered circles. We would combine these to create the great cosmic spirograph that never missed a prediction. It was so complete and so accurate that it was given a name that combines the Arabic al, the, and the Greek magest, coming from the word for magisterial. So the book was simply known as the Great Work. This was the state of science at the beginning of the Christian era. We find important advances during this period among Indian scholars, especially in mathematics, Chinese scholars, largely in medicine and mathematics, and Muslim scholars in astronomy and physics. These traditions developed in accord with their own cultural contexts, but as a result of global trade, there's still a Greek heart in the development that came after. In Western Europe, we see the Dark Ages at this time, during which little of scientific interest emerged. What's important to our story, however, was the rediscovery of philosophy by the early church fathers. Augustine, in the 5th century, finds in Plato an intellectual foundation for Christianity, one that would systematize it and philosophically justify it. Recall that Plato conceives of a bifurcated world. On the one hand, we have the material world around us, a false, corrupted representation of reality. Whereas on the other hand, we have the world of forms, a non-material world of perfection, right? This picture was easily tweaked to map onto Christian theological teachings in which reality is comprised of two realms. One, a sinful, diseased world of flesh, and two, an eternal, perfect world of spirit. So, following Augustine, there was a strong line of Christian Neoplatonic thought. But the rediscovery of Plato led to the rediscovery of Aristotle, and a division within the church arose over which Greek thinker ought to provide the philosophical basis for Christian thought. It was sort of the taste great, less filling debate of the time. The Aristotelian line is most closely associated with the Dominican friar Thomas Aquinas, whose views, Summa Theologica and Summa Contra Gentiles, shaped Aristotle to fit Christian belief. Aristotle, for example, has no creation event. The circular orbits of matter made from ether have been happening for an infinite time and will continue to do so. This, of course, would not do for Aquinas. So, Aristotle's prime mover, the ultimate cause of the circular motion, became a first cause, the creator God of the Old Testament. Soon after his death, Aquinas was condemned as a heretic for these views, and his works were banned from being taught in Catholic contexts. But they persisted amongst the Dominicans, and when the Dominican Pope John XXII took control, Aquinas was made a saint, and his works official church doctrine. The picture of reality at this time is one in which there is an earth created by the Christian God, and which operates, as Aristotle describes, by God's will. Aristotle's view of the world was not only taught, it became enforced. The questioning of this Aristotelian worldview was the hallmark of the scientific revolution. Nicholas Copernicus is the first major figure to present a substantive challenge. Ptolemy's augmented Aristotelianism, with its epicycles, eccentricities, and ecliptics, was flawless in terms of predictions, but it was a bear to work with. Copernicus figured out an easier route. Move the Earth from the center of the universe and have it and the other planets orbit the sun. Not having the Earth as the center of creation was a heretical denial of Aristotle and an insult to God's creation. So, when Copernicus's book on the revolutions of the celestial spheres was published, just before his death, it had an introduction added by a member of the clergy who warned that this should not be taken as a true description of the universe, but simply as a mathematical tool for easier calculation of observable astronomical phenomena. But the challenge was clear. It was simpler, it was more elegant. It didn't do away with epicycles, but it needed many fewer and allowed the eccentricities and ecliptics to be jettisoned. This elegance certainly smelled of truth and not just utility. This is not to say it was an open and shut case. There did seem to be good reason to reject the Copernican vision, right? Aristotle said objects move straight down when dropped. So, if you face in the direction that the Earth is moving, then everything that falls ought to drop behind you because the Earth would have moved forward while it was falling straight down. But we don't see that. Secondly, you ever drive with the windows down? What do you feel? A breeze. If the Earth is moving, then there ought to be a constant wind in one direction. Yet, there's not. This sort of objection, coupled with theological might embedded in our view of reality of a stationary Earth, the center of the universe. But the Copernican view became more and more popular among the educated, with Galileo Galilei becoming a significant proponent. Galileo was bold and unrepentant in his scientific work. He wasn't the inventor of the telescope, but he was the first to use it for serious scientific work. In his book, The Starry Messenger, he documented all the observations he made that contradicted Aristotle. His detailed drawings of the surface of the moon are astounding for their beauty and their detail. He shows mountains, he shows craters, and since Aristotle said things made of ether had to be perfectly spherical, those defy the Aristotelian worldview, right? That the moon is made of ether and therefore has to be perfectly spherical. He discovered the moons of Jupiter, which showed that contrary to Aristotelianism, not everything orbits the Earth. And, discovering the phases of Venus, he showed that shadows cast prove that it couldn't be orbiting the Earth, but would be expected and easily explained if both Venus and the Earth were orbiting the Sun. Galileo's work on Copernicanism caused him to be brought before the Inquisition. Twice. Convicted, he was sentenced to house arrest, where he turned his attention from astronomy to physics, particularly the physics of motion, what we call mechanics. Now, this had been his focus earlier in life when he did work for the military on projectile trajectories. These were needed for aiming cannons. But his later work was not just practical. It was importantly mathematical and theoretical. He showed that objects fall at the same rate, regardless of mass, and created equations to describe this motion. The mathematization of physics was a crucial step in the advancement of science. It was realized that the mathematical tools we had at the time weren't strong enough. However, and in the following generations, René Descartes developed analytic geometry and Isaac Newton created calculus, giving scientists increasingly powerful methods to develop mathematical theories to describe the working of the world. Now, Johannes Kepler, a contemporary of Galileo, took the data of the Danish master astronomer Tycho Brahe and worked to find an account of planetary motion that would rid humanity once and for all of these epicycles, the circles on circles. By trial and error, Kepler worked and worked until finally he hit upon the shape that worked. Elliptical orbits with the sun at one focus. That, turns out, would perfectly fit the observations. Kepler derived 3 numerical laws, setting out not only the shape of the orbits, but relations between the distance from the sun and the period of revolution. They were stunning results, but no one knew why they would be true. Aristotle's circular orbits had a philosophical basis, right? The perfection of the ether from which everything out there was made. The Church's adherence to the circles of their modified Aristotelianism had a theological foundation. But why ellipses, right? An egg shape, why? It was an open problem of the highest order. It was an anomaly in the classical paradigm. None of this was revolutionary. The basic concepts which ordered the universe and the picture of reality they gave rise to had become wobbly, but had not fallen. Until Newton. Isaac Newton developed the simple theory. 4 basic laws, 3 laws of motion and the law of universal gravitation. Newton's first law of motion concerns any object that has no force applied to it. An object not subject to an external force will continue in its state of motion at a constant speed in a straight line. Now, suppose I'm on ice skates, right? I'm just standing in the middle of the rink. What's going to happen? I'll stay in the middle of the rink. But if I'm on ice skates and moving forward at 2 miles an hour, I will continue to move straight ahead at 2 miles an hour until something pushes me or stops me. So the first law describes the behavior of an object subjected to no external force. The second then describes the behavior of an object that is subjected to an external force. So again, if I'm on ice skates moving forward at 2 miles an hour and you push me from behind, I now go faster in the same direction. If you pull me from behind, I slow down. If you body check me from the side, I change direction. The bigger the push, the more the change. The heavier the object, the less the change. So, an object is either subject to a force or it isn't. So the first two laws are sufficient to describe its behavior. But what about the thing that applied the force? What happens to it? The force I feel from you is felt by you in the opposite direction, but in the same amount, right? Again, if I'm on ice skates and you push me, I accelerate forward because of the force, and you go backwards because of it. If you body check me from the side, I change direction, and you go the opposite way, to the penalty box. To every action, there's always an equal but opposite reaction. These three simple laws explained a lot, but they become incredibly powerful when combined with the fourth law, the law of universal gravitation, which says that gravitation is an attractive force, a very attractive force, the Marilyn Monroe of physical forces. Take any objects with mass, and there will be an attraction between them along the lines connecting their centers of mass. This pull will be proportional to the product of their masses. Make one twice as heavy, twice the attraction. And it will be inversely proportional to the square of the distance between them. Move them twice as far away, feel only 1/4 the pull. When these three laws of mechanics and the law of universal gravitation are used together, we suddenly have an explanation for Kepler's elliptical orbits. Not only that, we could explain the tides, the motion of cannonballs, apples, virtually everything we see in the world around us. This theory was a monster. When Edmund Halley, a friend of Newton's, used it to predict the coming of a comet, it was hailed, rightly so, as one of the greatest achievements of the human mind in all of history. Not only was it successful in terms of explaining and predicting, but theoretically, it undermined the old foundation. Aristotle. Aristotle said that an object's natural state of motion is at rest in its natural place. Newton has no natural places and says that its natural state of motion is in a straight line at a constant speed. Aristotle says that objects move themselves, seeking their own natural place. Newton says that an object can't move itself. Aristotle gives completely different accounts for the motions of objects close to the Earth and heavenly bodies. Newton's law of universal gravitation is universal. It applies to everything equally. Aristotle's worldview was enforced by the centralized power of the Catholic Church. Newton's worldview came not from authority, but from observing, something anyone could do. And so Newton's success supercharged an intellectual movement developing around him, the Enlightenment. The picture of reality that emerged from the Enlightenment is one in which the universe is well ordered according to principles that are accessible to the human mind. We live in a world we can understand. Humans are perfectly rational beings made to understand the world we inhabit. Since rationality is the hallmark of humanity and all people have it, then none of us is better than any other. Human equality is a basic axiom. This stands deeply opposed to the hierarchical structures found in religion and the monarchical governments that were the holders of power at the time. The Enlightenment gave to all people the ability to understand the world. No longer were we subservient to superior authorities if justice be done. We didn't need to be told the truth from above. There is no one above, and we could discover the truth ourselves. Let all of us hear the arguments, and we'll select the best ones ourselves. When it comes to the distribution of political power, let us vote. Since humans are rational, we'll select the best person to oversee the implementation of laws. If humans are rational, our choices will reflect that. We all feel pleasure and pain, preferring the pleasurable to the painful, and so we will act as perfectly rational maximizers of pleasure over pain. Put us all in a marketplace, and we will all act to bring about the best consequences for ourselves. Since our best interests are often at cross purposes, I want to spend as little as possible on the sandwich I'm buying from you, while you want to charge as much as possible when selling it to me, there will be rational, predictable prices, governed by forces in the marketplace that look exactly like Newton's forces on billiard balls. Like Newton, we just need a combination of observation and reason to derive what must happen. This is the picture of reality we get from the Enlightenment in the 17th and 18th century. We live in a well-ordered, predictable universe full of things we can observe. We exist in it as perfectly rational agents, capable of observing everything there is, capable of using our reason to find the laws that govern their behavior. As such rational agents, we too become predictable, allowing new human sciences to explain how we behave. Needless to say, this view did not please everyone. There were those who thought that it took the mystery away from the world, mystery that gives meaning. Humans were reduced to robots with no passion or love. The romantic backlash of the 19th century strove to put the irrational back, front and center as the basis for true humanity. What makes us human is not that which makes us glorified billiard balls, but that which sets us apart from the rest of the world. We make and appreciate beauty. We have free will, which we exercise in ways that are often capricious and bizarre. We're not just numbers, we're romantic beings, full of life in a universe that hides the unknowable deep at its core. This was the battle over the shape of reality that was raging at the start of the 20th century. The Enlightenment ideals, with the scientific advances they generated, had given rise to human progress, as was seen in the incredible advances in every field of scientific endeavor and the emergence of democratic states with market economies. The Romantics objected, but the scientists had their supporters. They marched on. And then, as the 20th century dawned, the cracks started to appear. Strangely, they arose in the last place anyone would have suspected: mathematics.